Now all the gadgets that we use these days are becoming more and more into the digital domain. Okay, earlier it used to be analog devices, say for example telephone. It used to be an analog device earlier, but nowadays it is a digital device. Television is another example, or radio is another example. It used to be an analog device, but these days it is becoming a digital device. Communication is more going into computer networks, which is again a digital domain. So you can see that in everyday life digitalization is happening, and there is a big drive for it. The reason for this is because processing of signals become very easier if they are in the digital domain. You can store it very easily, you can manipulate it very easily, and not only that, you can avoid noise, interference of noise with whatever data that you are storing or processing. It is very easy to remove those noise, and so there is a lot of advantages of going into the digital domain. So that's why every gadget that we use goes into the digital domain. Okay, now if you consider the basic difference between an analog signal and a digital signal, okay, the naturally occurring signal, all the naturally occurring signal are analog and analog continuous time signals. All the naturally occurring signals are analog continuous time signals. Okay, for example, the voice that I am speaking to you. So if you look at the output of a microphone, this is basically an analog signal which varies in amplitude continuously. Okay, any value of amplitude is possible in principle, and for every time there is a particular magnitude. So if I represent say voice signal, then you can see something like that, right? So depending upon the speech, wherever loudness is more, then the amplitude is more. Where there is more quietness, then the amplitude is lesser. And so that is basically an analog signal. Why do we say it is an analog signal? So this is time, and this is the output of a microphone where I plot the voltage as a function of time. So the reason why it is analog signal is because if you look at the y-axis, so y-axis is basically the amplitude of the signal. Okay, so t here is the independent variable, and v of t is the dependent variable. Okay, you know the difference between dependent variable and independent variable. That means voltage varies as a function of time, or the voltage at a particular time is a function of time. Okay, so now if you look at the dependent variable, so in order to say whether a signal is analog or digital, what you need to look at is the dependent variable, not the independent variable. Okay, so if so a signal is said to be analog, if the dependent variable is allowed to take any magnitude. Okay, if the dependent variable is allowed to take any magnitude, for example, here I have not given any scale here, but I can add a scale here. Okay, so this is the amplitude scale. It could be going into the negative direction also. So there is a 0, then maybe some 0.1, so there is a 0, then 0.1, 0.2, 0.3, 0.4, 0.5, etc., and minus 0.1. It could go to the negative direction also. Okay, so these are basically telling the magnitude or the amplitude of the signal. And if you look at the value which the signal take at any time, it could be anywhere in the range that you see here. So if you take if there could be usually a maximum limit to which the output is allowed to take, and there would be a minimum value also. So within that range, say from 1 volt to minus 1 volt, within that range it is allowed to take any value. And how many values are there? Infinite number of values are there. So there are infinite possibilities for the amplitudes, and it is allowed to take any of those infinite possibilities. Okay, so if the dependent variable is allowed to take any magnitude, that is one of the infinite possibilities. Okay, so dependent variable is allowed to take any magnitude means one of the infinite possibilities. Then we call the signal as analog signal. Okay, on the other hand, if you look at a digital signal, how does it look like? Okay, so let's plot a similar example. Let me draw another graph. Here also I am going to put some scale, maybe similar scales, 0, 0.1, 0.2, 0.3, 0.4, 0.5, and say minus 0.1. Okay, so this is exactly the same levels which I earlier showed, but I told you that analog signal is allowed to take any value between these different levels I pointed out here. Now if I look at a digital signal, what it means is that it can so it goes like this. Okay, so there are various levels, and the amplitude of the signal is confined to those levels. It is not allowed to take anything apart from those levels. Sorry. So at any time you have the signal taking values which are in one of those predefined levels. So this is basically a digital signal. Okay, so this definition should be very, very clear. Most students confuse this. They don't know exactly what is digital and what is analog. So digital signal means it is allowed to take we have to look at first of all the dependent variable, and then dependent variable is allowed to, if it is allowed to take infinite in any possibilities in the infinite possible values, any one of those possibilities, then it is called analog signal. But if it is restricted to some finite number of levels, voltage levels, okay, then it is called digital signals. Okay, I hope that is clear now. Okay, so then there is a different classification. So this is what is called a digital signal. This is a digital signal. Okay. Now I also want to classify signals into, signal can be classified in different way also, that is continuous time and discrete time. This is also a classification which often students confuse with analog and digital. Okay, signals can be classified as continuous time signals and discrete time signals. Now, what do we mean by this classification? Now, here we look at the independent variable, that is the time. Okay, so you look at the independent variable. The earlier example that we saw so is again an example of continuous time. Okay, so you have some variation of signal, so voltage is varying with time. Now we are looking not on the dependent variable, we are looking at the independent variable, and you see that any value of time, it has a value. It is not restricted to some particular instant of time. The signal has value for all instants of time. So continuous time signal means so this is number 1 and this is number 2. So number 1 definition is that the signal has a value assigned for all instants of time, or you can say independent variable. Okay, the signal has a value assigned for all instances of independent variable. Example, time. Now, what is discrete time signal? So discrete time signal, if you look at, so here also you can say there is a time axis, but not all instants of time it is allowed to take values. So there are certain instances where the signal values are defined. Usually they are uniformly spaced. It could be well extended to the negative side also. Okay. So this is 0 time, and then you have say delta, 2 delta, 3 delta, 4 delta, 5 delta, etc., and this is minus delta. So delta is basically some small value of time, and its integer multiples is the instance at which the signal is allowed to take. So the same signal, if I represent using the discrete as a discrete time signal, then it will take values like this. Okay, this is the value it takes. Now here it is taking this, and it is taking this. Now you look at the y direction, that is the dependent variable direction. It is still is allowed to take any amplitude. There is no restriction there yet. Okay, so this is an analog signal still. Okay, so usually this is why the confusion arises. Students would say that this is not an analog signal, this is a digital signal. No, this is also an analog signal. Okay, only thing is that it is a discrete time analog signal. Okay, so what is the definition of discrete time? The signal is allowed to take values only at definite instance of independent variable. or time. Okay, so this classification into continuous time signal and discrete time signal should not be confused with the classification into analog signal and digital signal. Okay, so this is analog and this is digital. Okay, so signals can be classified into analog and digital. It could also be classified as continuous time signal and discrete time signal. Now, if you look at the process by which we convert analog signal, as I told you, all naturally occurring signals are analog signal. They have values defined for all instants of time. Therefore, it is also a continuous time signal. So, it is a continuous time analog signal, and the magnitude or the amplitude which the signal would take could be anything in a given range, depending upon the dynamic range of the signal. For example, the voice that we take, we can't maybe extend our voice beyond certain amplitude. There is a limitation how loud we can be. So there is an inherent limitation. So, but from the smallest voice to the peak voice that we have, there is a range. But between that range, any value of loudness is possible. All right. Now, how do we convert analog signal, continuous time analog signal to digital signal, or how do we convert the analog signal to digital signal? So let's do that. Analog to digital conversion. I would like to say the basic concepts involved. I am not going into the detail of it. That is entirely a different, altogether a different topics which later we will come across in maybe other courses. But here just I want to give you the basic idea behind it. So as I told you, you have a signal which is something like this. So this is time and this is the voltage as it varies with time. Now this takes all the values possible in a given dynamic range. Now to convert this, there is a two-step process. The first step is basically called sampling. Okay, so we'll go through the first process, which is called sampling. Okay, what essentially is sampling? Sampling is basically converting the given continuous time analog signal to discrete time analog signal. It is going to be still analog. We still don't have a not exactly like that. So let me just draw a. So this signal, what I do is I take sample. That means I look at a particular instant of time with some period, I sample it. So there are circuits for this. Basically, you just take what is the value at a particular instant of time. You connect it to a capacitor and then disconnect the signal from the input of the capacitor. So whatever is the voltage to which the capacitor gets charged, so that will remain until we take the next sample. It will remain like that. So basically this signal, if you look at so after sampling, so it depends upon the detail of the circuit, how exactly after sampling it will look like. It could look like this also. That means this is basically an output of a sample and hold circuit. This is not exactly the original signal, but some version of it. Okay, so we have sampled it. That means basically we have taken the values, but then whatever values that we have sampled, we hold it until the next sample. Then again we sample after some definite interval of time. and then that value will be held and then until the next sampling, and that way. So that way the signal will look like. So now we can remove this vertical line here, that's not necessary. Okay, so this is an example of. Okay, so this is the kind of signal that we will get after sampling. Now, so is it basically a digital signal? No, it is still a continuous time signal because we are holding that value until the next sample. So this is basically output of a sample and hold circuit. Output of sample and hold circuit. It basically involves a switch and a capacitor. Okay, so we have sampled it, so we have modified the original signal to some signal which has some sort of steps, and the reason why we got is because we are only sampling after every definite intervals of time, and that definite interval of time you can call it as delta t or something like that. It could be 1 millisecond, it could be 1 microsecond, depending upon how accurately you want to have the signal look like after the sampling. Okay, so this is step 1. Now what is step 2? Step 2 is called quantization. So that is quantization. Quantization means we have this analog signal which will be converted to, so that means we have to define predetermined level here. So only these levels are allowed. So here if I draw these lines, so you can see that here the signals have different values which it is having, but they are not necessarily falling in one of these levels because it could be anywhere as it is an analog sample. So but after sampling, when you do the quantization, you assign the magnitude to the nearest value, nearest level. Okay, so for example, this particular level is more near to the upper level, that is level. So if I call this as level 1 or 0, 1, 2, 3, 4, 5. These are different levels. So similarly here also 0, 1, 2, 3, 4, 5. Okay, so whatever is the nearest level, so it is like the first in the first interval I have shown, that is in the negative side, the amplitude is basically between 1 and 2, but it is more near to 2. So therefore what will I do? I will assign to the nearest level, which is 2. Then it is almost at 2, so it will continue to remain at 2. So this is the way after quantization. After that it is little above 3 but less than 4, but you can see that it is more near to 3, so it will be assigned to 3. Then after that you see it is more near to 4, so it will be assigned to 4. And then next one is more near to 4, the next 2 interval, the signal is more near to 4 than to 5, though it is between 4 and 5. So it will continue to remain in 4. Again the next one is also more near to 4, and then it is more near to 3. It is between 3 and 2, but it is more near to 3. The next one is more near to 2. So it will go to 2. Okay, so this is basically now a digital signal. Okay, so these are the steps. So first you do sample and hold circuit will basically take a sample and then keep that value, hold that value until the next sampling instant, and then again we have a value. So value is not changing within that interval between two sampling. Okay, whatever sample that we took, that value will remain, but then that value necessarily doesn't fall into one of those predefined levels for a digital signal. So therefore we need to quantize it in order that the value will be constrained to one of the predefined levels. So that process is called quantization. So I hope now it is clear. So we have, yes
sir, how do we calculate the intervals of the levels, sir?
I mean, you are talking about this say these
Zero.
this
Yes, zero.
yes,
Yes,
so
sir.
so this are decided by the so for example the accuracy. Okay, so how accurate your digital signal representation of the actual signal. That means if you want to reduce the error as much as possible, you can reduce this difference between two successive predetermined amplitude levels as small as possible. That will make it a more closer representation of the actual signal. Similar, two things are there. One is the sampling interval. The other is basically the amplitude interval. Okay, so let me just categorically write this here as a note. So the delta t, this is the sampling interval. Okay, sampling interval. So if I could show it here, this is your delta t, and delta v, okay, which is basically this. So the delta t, this is basically the quantization interval. Okay, the delta t and delta t values should be small enough to have a faithful representation of the original signal. Okay, so that's basically. So nowadays earlier we used to have the normal telephone call, but nowadays VoLTE telephone calls, right, we can make, like almost all network is now introducing VoLTE. So that where basically these signals are basically converted into digital form, and then it is it goes to the communication channel, and then basically this signal finally get into your loudspeaker. This quantized signal, sampled and quantized signal is what is coming into the so if you basically make this delta t and delta v very small, then you won't find any difference in quality with respect to the actual signal. Okay, so you can make it as small as possible, but the cost that you need to pay for is that you will have to transmit large amount of data. So that's what I am coming into. The amount of data that you need to transfer from one point to the other will depend upon these two things. One is delta t and the other is delta v. Okay, so let's take an example. If there are 256 voltage level if there are 256 voltage level, then for binary representation of each amplitude, voltage amplitude requires, as last class we studied, it requires 8 bits, right? If there are 256 voltage levels, then for binary representation of each amplitude requires 8 bits. Then if, let me write it as a separate sentence, so this is 1, and then if there are n samples per second, then in 1 second we will have n into 8 bit of data to be communicated. Okay, so if you have 256 levels, we can represent that which of those 256, we did that problem, that how many bits are required, or how many bits of information is there in order to tell which of the 256 levels the signal is going to fall in. Now that is for one particular instant, one particular sample. It could be for any interval, so it could be like in this interval or in the next interval, 0, 1, 2, 3, 4, 5, 6, 7, etc. So in each of this interval you will have a 8 bit. We don't know in advance what it is going to be, but it would be in one of the 256 level that we know. But in order to specify which of the 256 level it is going to be, we require 8 bits. Now depending upon delta t, you will have in 1 second say so 1 by delta t, right? 1 by delta t. So this n is basically 1 by delta t. So delta t is the duration of the interval between two sampling, and then in 1 second if there are n samples, means that n is what? 1 second divided by delta t. Okay, so I can also write it as n is equal to 1 by delta t. Okay, it's like 1 by time period is basically the frequency. So if there are n okay, so so this much is the amount of data. So let's put some value for n. Say suppose if therefore if n is equal to say 10 raised to 4, if n is equal to 10 raised to 4 in 1 second, then that means 10 raised to 4 samples. Usually for voice signal this is a typical value, okay, because the frequency of voice signal can go up to 20 kilohertz, which is basically 2 into 10 raised to 4. So at least 10 for a reasonable quality of sound, you need at least 10 raised to 4 samples. So n is equal to 10 raised to 4 samples per second. So therefore the data per unit time, or unit time means per unit second, is basically 8 into 10 raised to 4 bits per second. Okay, now if you want even more accurate signal, what you need to do, instead of 8 bits or instead of 256 levels, you can think about going into say double of that, that is like 512 levels or 1024 levels. So you can keep on increasing the number of levels. Usually it is gone in the it is taken in the power of 2, because ultimately we are going to take all these magnitudes in binary form for processing it, and therefore we if at all we are increasing the number of levels, we usually go it in the power of 2. So 256 is an example, which is 2 raised to 8. So we require 8 bits. If you have 9 bits, then 512 levels are possible. If you want to make it even more better approximation, that's what is happening in a high definition or a high fidelity, we would say high fidelity audio signal will have a large number of possible levels, and thereby the quality of the audio will be very good, and also the sampling rate. Same thing can be said about video signal, where you have the signal is not just depending upon time, but also in x, y and time. Same thing can be said there. We will talk about what is called as the frame rate. That means how many frames it changes in 1 second, and then the resolution for each frame. These are the two things. That means the number of the pixels in one frame. So usually it is something like 108 1080 1080 by some 856 or something like that. Depending upon the aspect ratio, the number of pixels will differ, and then we need to change it in 1 second. At least 16 frames should be there in order to in order for us to feel it as a movie, right? A continuous varying signal. So usually 30 frames per second, 50 frames or 60 frames per second, these are common. So minimum is usually a 30 frames per second, but each frame that will depend upon how many pixels we are talking about. So you can calculate the same thing for a video signal. If it is a black and white signal, each pixel can take one of the 256 grayscale. If it is a color signal, then each pixel have a red component, green component and a blue component, and each of them can be in one of the 256 level or one of the 512 levels. So that way a video signal will have huge amount of data. So for same duration of time, if you store a song, it will take much lesser space compared to a video for the same 1 hour duration, right? So you can basically calculate how much is the data. So there is always a trade-off between the amount of data that is required to represent the signal and the quality of the signal. So if you try to increase the quality, what will happen? So there is a trade-off. The trade-off is between the quality and we will call this as the bandwidth. Okay. So if you want to increase the quality, you have to increase the bandwidth. Okay. But increasing the bandwidth, so the requirement of bandwidth for high quality, you need a high bandwidth. So that means large number of data need to be communicated. But if you reduce the I should say maybe when I say as a trade-off, I should say like the speed. Okay. So speed, like if I increase quality, what will happen? The speed will go down, right? Because you need to transmit more amount of data. So if the bandwidth is fixed or limited, then the speed will be reducing as you increase the quality. So there is always a trade-off. So depending upon how much bandwidth we have, so like if you compare with our earlier 3G connections, the quality was very compromised because the speed was less. But now in 4G we have a larger speed, and therefore the quality with which we can watch a streaming of a video is very good. And similarly, if you go to a broadband connection, then we have like say 100 mbps or 1 gigabits per second connection, then you can have high definition video possible. So there is always this trade-off. So more quality that you require, then you need to pay for it. That is the more bandwidth is going to be required. If it was a fixed bandwidth, then your speed will go down. Okay, I hope it is clear so far. Any questions so far? Okay, so now let's take a break, and we'll come back in 5 minutes.